So now we are going to see what are the different types of the ligands. We came to know that ligands are the one which are donating the electrons. That is, in simple words we can say that ligands are acting as what? Lewis bases. That is, they are donating the electrons. Depending upon their donor atoms, now we are going to classify the ligands. So first important classification is called as what? Unidentate ligand. So basically here you can just see that, so whenever a ligand is bound to the central metal ion through a single donor atom, that is only a one pair of electron which is able to donate. For example, is that of your Cl minus. So this, when you're saying, this is acting as what? Unidentate ligand, because it is having just a pair of electrons, single donor atom. Similarly, your water, H2O. So here is a neutral molecule, but here the lone pair of electrons which is present on the oxygen, so that is able to donate a single pair of electron and a single donor. So whenever they are binding the central metal atom or the ion to a single donor atoms, so they are called as what? Unidentate ligands. The another important classification of the ligands is called as what? Didentate ligand. So when a ligand is bound to the metal ion through the two donor atoms, it is called as what? Didentate ligand. Here they are giving you an example. Basically ethane 1,2 diamine. You could just see the structure over here. NH2, NH2 which has been bonded to CH2 and a CH2. So basically we could see that there are two lone pair of electrons on the each nitrogen atom. For example, if I will ask you, so if I take an example over here, CO which was bonded to here, Cl, 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 Cl. So what is happening over here? A single donor atom is binding your cobalt. So that was called as what? Unidentate ligand. For example, in a didentate, whatever they have given you, didentate, I'll take an example of En. And we have seen the structure. En is nothing, which is called as what? Ethane 1,2 diamine. Okay, diamine. So here we have noticed that it is having the structure as NH2, CH, CH2, CH2 and NH2. So when you're noticing its bonding with respect to the cobalt, you could just see that, remember this overall is one molecule. So overall it is donating to your cobalt. So what it is happening? So these are the ligands in which you can just see that there are two donor atoms. Two donor atoms which is binding to your single central metal atom or the ion. Whereas in the unidentate we could see that there is a single donor atom. Whereas in the didentate we could see that there are two donor atoms. So that will be called as what? Didentate. Another example you can also see, the most familiar one is also called as an oxalate, C2O4 2 minus. So what happens over here, you will be having in this way, COO minus and a COO minus. So when it is bonding, you could just see that this overall is a one molecule. But when it is donating, it is having a two donor atoms which is binding your single central metal atom or the ion. So that is called as what? Didentate. So unidentate means which is binding your central metal atom or the ion through a single donor atom. Okay. Didentate ligands means the ligands which are binding to your central metal atom or the ion through the two donor atoms. Similarly, which is also called as a polydentate ligands. So poly, uni means one, di means two, poly means instead of saying it's a tri, tetra, penta, we're just using a common word as poly, that is having more than two donor atoms. The major familiar example is called as your EDTA, which is called as ethylene diamine tetraacetate. Ethylene diamine tetraacetate. So basically when you are seeing a structure, we could just see that here. You can notice over here, instead of writing it, CH2, CH2, NN, CH2, COO minus, CH2, CO minus, CH2. So you can just see over here. So it is written as EDTA4 minus. So actually what happens, instead of here COO minus, first it would be having a COH, COH, COH and COH. So when you're dissolving it, they will be giving you the respective ions. So utilizing all these 4 groups, it is going to bind your single central metal atom or the ion. So generally we can call it as a tetradentate. But since it is having more than 2, we are calling it as what? Polydentate ligands. So the ligands which are having the capacity to bind the central metal atom or the ion with respect to more than 2 donor atoms. So that is called as what? Polydentate ligands. So major classification of the ligands you have to remember is unidentate, didentate and polydentate. With respect to this classification, now we are going to see some other classifications of the ligands, which you are going to see over here, which is called as what? Chelate ligands. So chelate ligands are nothing. So they are actually the didentate or polydentate ligands itself, which is using its more than 2 donor atoms, which uses 2 or more than 2 donor atoms to bind your single metal ion. So here is an example. Here is the same thing, didentate or a polydentate ligands which are using more than 2 donor atoms to bind a single central metal atom or the ion. Can I ask me, sir, why we have to deal with it? So basically when you are going with the stability of the complex of the concept, that concept, we could just see that they can ask you. For example, they will be giving a COCl4 is much stable or COCl4 is more stable or COEN4 is more stable. So merely by seeing nobody can see, but you have to make a notice over there that whenever a didentate or a polydentate ligand is present, it increases the stability of the ligands, and when such a stability is increased in the presence of such a didentate or a polydentate ligand, that is called as a chelating effect, which increases what? The stability of the complex. So chelating ligands means nothing, they are the didentate or a polydentate ligands which uses 2 or more donor atoms to bind a single metal ion. So as the stability of the complex increased due to this chelation, that is called as what? Chelating effect. Coming with respect to the denticity, for example, if you have been asked that what are the number of the chelating groups present, of course here how many groups are present? There are totally 4 such groups are present. So denticity just gives you the number that what are such chelating groups present in a complex. Okay. The next important classification of the ligands, it is called as ambidentate ligands, which is one of the most important and also a noteworthy point to remember. So ligands which contains more than 1 donor atom but can donate only 1 at a time is called as what? Ambidentate ligands. Able to notice what is the difference? So they will be having, so these are the ligands which will be having more than 1 donor atoms, but at a time they can only donate only 1 at a time. That are called as what? Ambidentate ligands. For example, here they are given you with respect to a NO2 minus. Here you could notice that, so these ion can coordinate either through oxygen or through nitrogen, but at a time only one of the donor atom is binding your central metal atom or the ion. So these are called as what? Ambidentate ligands. You can just see over here, N is binding to your M. Though it is having, N is also a donor atom, oxygen is also a donor atom, but at a time you could just notice that only nitrogen is binding your metal, and in the second example we could notice that only oxygen is your binding your metal. So ambidentate ligands are the ligands which are having more than 1 donor atoms. Nitrogen or oxygen, both are the donor atoms, but can donate only 1 at a time. So they are called as what? Ambidentate ligands. So when it is binding to the nitrogen, it is having a name of nitrito-N. When it is binding to the oxygen, it is called as a nitrito-O. Similar example is your thiocyanate, SCN-. Here both your sulfur as well as that of your nitrogen is acting as your donor atom. But at a time what happens, when a sulfur donates, that is called as a thiocyanate. When a nitrogen donates, that is called as an isothiocyanate. So ambidentate ligands means what? Which are having more than 1 donor atoms but can donate only 1 at a time. So they are called as an ambidentate ligands. The next major definition we have to go with, which is called as what? Coordination number. So coordination number means nothing Just it is the number of the donor atoms of the ligands to which the metal is directly bonded. For example, if I give an example that give the coordination number of COCl4. Yeah. For example, I'm just giving you the COCl4 2 minus little because I want my cobalt is having a state should be minus. I will be dealing with it later. But what is the coordination number of cobalt over here? So they say what? So please note over the number of the donor atoms. They are not just saying that the number of the ligands. They are saying that the number of the donor atoms of the ligands to which the metal is directly bonded. Since our here chloride is what? A unit-entate ligand. So it is having how many donor atoms? One chlorine means one donor atom. So such chlorines are how much are there? Totally 4 are there. So coordination number is 4. Similarly, if you can go with your PtCl6 2 minus, here also we could just notice that. So here we can notice that you are having 6, since chlorine is your monodentate or unit-entate ligand. So here the coordination number is 6. Similarly, when you are going with your NiNH3 4 2 plus, of course here ammonia is also your unit-entate ligand, a single donor atom, that is through your nitrogen. So it is also having the coordination number of 4. But in case if I have given an example of FeC2O4 thrice 3 minus. Of course here your iron is your central metal atom and your oxalate is what? Your ligand. So what is the coordination number? Of course, if anybody says that it is 3, it is wrong, because we are now, as the definition, what it is saying? Number of donor atoms of the ligands. Here also, oxalate is what? Didentate ligand. Yes, the ligand which is having 2 donor atoms. That is, each oxalate is having the 2 donor atoms. So how many such oxalates are there? 3. Since each oxalate is having the ability to donate 2 electrons, the total coordination number will be 6. Able to understand? So each oxalate is a donor atoms. How many? Each oxalate is having 2 donor atoms. So what does your coordination number says? Number of the donor atoms of the ligand to which it is bonded to your central metal atom or there. So such donor atoms is how much? 3 are there. But each oxalate is a didentate. So the total coordination number will be 6. Similarly, can you give me this one? COEN thrice 3 plus, what will be the coordination number? Of course, here En is also a didentate ligand, so you will be having the coordination number as 6. So this is very much important to calculate your coordination number. So please remember that it is said that it's the number of the donor atoms of the ligand to which the metal is directly bonded. The next most important definition we have to deal with, which is called as a coordination sphere or a counter ion. To deal with it, let me take an example. It's the same example. Let me take K4FeCN6, which we have dealt further. Just to remember, coordination sphere means, so whatever the atoms which is present within the square bracket, they are called as what? Coordination sphere. That is, a coordination sphere is nothing. It will be constituting your central metal atom and some specific number of ligands which will be enclosed within this square bracket. So this is called as what? For example, if I'm going to write it, FeCN6 4 minus. So this will be called as what? Coordination sphere. Whereas the part which is outside the square bracket, so that will be called as what? As your counter ion. Will be called as your counter ion. So whatever which is there within the square bracket, so that itself a central metal atom are the ion and that of a specific number of the ligands. So overall that will be called as a coordination sphere, and this one K plus which is present outside the square bracket, that will be called as your counter ion. Then the most important thing I would like to deal with is called as that of your oxidation number. Since in the redox part we have dealt with it, how to calculate, the same thing we are going to see over here. There is a charge the central atom would carry if all the ligands are removed, along with the electron pairs that the charge shared with the central atom. Just you have to remember how to calculate it. So basically, if I am giving you the example, you can ask me, sir, how did you write this FeCN6 4 minus, you can ask me. So basically, when you're writing K4 and FeCN6, of course it will be dissociating. I said that when you're dissolving in water, you'll be getting as what? 4K plus FeCN6 4 minus. Now, this is the part. But what happens if I want to calculate the oxidation number of the iron? That is FeCN6 4 minus. I found to calculate. How are you going to calculate? Let me take my iron as what? X. Cyanide means it is a cyanide ion, Cn minus. So X plus of each cyanide is having minus 1 charge. So it is having such 6 cyanide ions. So I will be having as minus 6. So overall it is having a charge of minus 4. Alva. So when I am calculating it, what happens? Minus 4 plus into minus minus. Yeah. So when it goes over here, plus 6. So in turns you'll be getting as X is equals to plus 2. So iron will be having over here as plus 2. Able to understand? So remember, whenever you're dealing with, while writing the name, you can just see over here one more example they have given you as CuCN4 3 minus. So oxidation number of the copper is plus 1. So whenever we are writing it, we are going to see in the nomenclature part, whenever you're writing the oxidation number with respect to the complexes, we are always using the Roman numerals. That is, you could see over here Cu1. So in this way. Similarly, in this case, when you're writing as Fe, we will be writing as Fe2. Able to understand the Roman numerals. Okay. The other part, which is called as a homoleptic and a heteroleptic complexes, that is nothing. If the complexes in which a metal is bound to only one kind of a donor groups, that is, you could just see that only one donor group, one kind of a donor group is present, they are called as what? Homoleptic. Whereas in a heteroleptic, you'll be having more than one kind of donor group. That is, you're also having chlorine, you're also having ammonia. So these are called as what? Heteroleptic. Homoleptic means only one type of a donor groups, whereas in a heteroleptic, you're having more than one type of a donor groups.